Previously, we learned how fuel and air combine and how mass is conserved during combustion, but knowing the reactants is only half the story. As engineers, we must answer an even bigger question. Where does all the energy go? Why do flames become extremely hot? And why can all chemical energy become useful work? In this arc, we will unlock the second pillar of thermodynamics, energy. In reacting systems, the substances themselves are changing. Free molecules disappear and new products are formed. Because of these chemical changes, tracking energy becomes more challenging. To solve this problem, engineers use a reference point called the enthalpy datum. Think of it as a starting line for measuring energy. The total enthalpy of a substance consists of two parts. The first is the enthalpy of formation, which represent the chemical energy stored inside molecular bonds. The second is the sensible enthalpy, which represents the energy associated with temperature changes. By combining these two components, engineers can determine how much energy is released during combustion. This also introduces us to heating values. The higher heating value, or HHV, assumes the water produced condensed into liquid and release additional heat. The lower heating value, or LHV, assumes the water remains as vapor, so the extra heat is not recovered. Therefore, HHV is always greater than LHV. Now that we know how to measure energy, we can analyze where it goes during combustion. The energy rate balance follows one fundamental rule. Energy cannot be created or destroyed. Reactants enter the system carrying chemical and thermal energy. Chemical reactions occur inside the control volume. Heat may cross the system boundary. Work may also be produced, such as the movement of an engine piston. Finally, products leave the system carrying energy in the form of enthalpy. Therefore, the energy equation simply asks, where did the energy go? Did it become useful work, or was it transferred as heat, or does it remain in the products? This equation forms the foundation of combustion analysis and is used to predict temperatures, efficiencies, and fuel requirements. Now we arrive at one of the most important concepts in combustion engineering, adiabatic flame temperature. Imagine combustion occurring inside a perfectly insulated chamber. No heat escapes to the surroundings or chemical energy remains inside the products. Under these ideal conditions, the product reaches the highest possible temperature. This maximum theoretical temperature is called the adiabatic flame temperature. It represents the thermal limit of combustion. This temperature is important because it affects efficiency, material selection, and pollutant formation. Generally, the highest flame temperatures occur near stoichiometric conditions. However, real systems rarely reach this temperature. Heat losses, excess air, incomplete combustion, and chemical dissociation or reduce their actual flame temperature. Therefore, the adiabatic flame temperature serves as an ideal benchmark for engineers. At this point, we have mastered the mass conservation and energy conservation. Now we unlock the final concept, entropy. Entropy measures the degree of irreversibility in the system. Every real combustion process generates entropy. Heat transfer, mixing, friction, and chemical reactions all contribute to entropy generation. According to the second law of thermodynamics, entropy generation can never be negative. This means not all energy can be converted into useful work. Some of it inevitably loses its works, producing potential. Therefore, the no real combustion engine can ever achieve 100% efficiency. To fully analyze a reacting system, engineers use three fundamental principles. First, mass conservation. Second, energy conservation. And third, entropy generation. Together, these principles form the complete thermodynamic framework for analyzing reacting systems. But one final question remains. Can we generate electricity directly from chemical energy without burning fuel at all? To answer that, we move into our final chapter, the fuel cell revolution arc.